Okay guys, I've got the notes kind of in front of me here, and again what we'd like to look at here is maybe some strategies to help you solve physics story problems, and you'll probably find it helpful to have a calculator kind of with you. The goal today also is to show you kind of another equation that we can use to help us, and some of the rationale reasons why. So we've really talked about several different types of motion: constant velocity motion, and we have our equation for that. This would be like a car with a cruise control. And then we've also have talked about objects getting faster and objects getting slower. That would be our acceleration. So we had a how fast equation, and then we had a how far. Hopefully by now you kind of have a good kind of understanding of these equations. We've talked about them a lot. How fast equation can determine speeds of objects. How far can determine how far objects have gone. Well, there's a third equation that is kind of helpful for acceleration. These are a couple here, but there's a third equation that we can use to kind of help us too, and I'm going to kind of work with you on that here shortly. Let's kind of do a little bit of practice here with how far and how fast before we look at that third equation. So let's say we have this sprinter, Usain Bolt. He accelerates. Okay, that means he's getting faster or getting slower. Okay, he accelerates from the starting line from rest at a rate of 4 meters per second squared for 3 seconds. Then he's traveling at constant speed. So I always like, on a story problem, I always like to underline or circle things that are important. So acceleration, or accelerates, that means his velocity is changing. Okay, he accelerates from the starting line from rest. Now that from rest is an important phrase. What exactly does that mean? Well, from rest means that he's starting out with an initial velocity of 0. So that phrase there really can be translated symbolically into VI equals 0. His acceleration then is also given. So since this is meters per second, or meters per second squared, this concept here, this number 4, then represents the acceleration. That's our A. Now it's positive, that means he's getting faster. He does this for 3 seconds. That's our time idea. So first off, we'd like to get how fast. You know, how fast is he traveling? Well, how fast is he traveling then represents our how fast equation. So we can write then VF equals VI plus AT. Okay, well, we know the VI we said was 0, so we can make that term go away. The acceleration then represents 4 meters per second squared. And then we have our time, times 3 seconds. One of the seconds cancels, and we're left in with 12 then meters per second. That would be his speed at the end of 3 seconds. How far did he run in those 3 seconds? Well, how far, that represents a delta x idea. Okay, how far? Displacement. So that's our how far equation. Delta x equals VIT plus 1/2 AT squared. Okay, well this term goes away, and we're left then with 1/2 times A. That was 4 meters per second squared, times the square of our time. Well, our time again is 3, but we have to square everything. So that becomes 1/2 times 4 times 9. Okay, so 1/2 times 4 is 2, times 9 is 18. 18 are seconds squared, and that will cancel out with these seconds, leaving us an answer of 18 meters. Okay, I always like to circle, underline things, you know, make sure I have my equations down on my sheet that can help me. Let's try this other problem. Let me scroll up here, make sure you guys can see everything. So a dragster starting from rest, okay, from rest, VI is 0, accelerates at a constant rate of 32. Okay, that's our acceleration, that's our A. How long? So how long in seconds, so that's a time idea. How long in seconds does the car take to reach a distance of 402 meters? Well, that distance or displacement's a delta x idea. Okay, so we'd like to figure out how much time would the car take given this acceleration to reach this far. So again, that would be our how far equation. Okay, there's our how far equation. And let me kind of scroll up here. Well, we know the VIT, the VI is 0, so this product will be 0, and we're left in with 1/2 times A times the square of our time. Okay? We're not sure what our time is, but we know then how far represents 402. Okay, so can you kind of work that out? Take 402 times 2, then divide by 32, and then take a square root. Here's where a calculator might kind of come in handy. So I'm going to turn it on here first, clear it. 402 times 2, divide by 32, and then I want to take a square root, or take it to the half power, so I get around 5 seconds. 5.01 seconds. How fast would this car be traveling after a quarter mile? Well, we can use then our how fast equation. Okay, we know again the A is 32. Our time now is around 5. Our VI was 0. So we can take 32 times 5. So that's going to be about 160, right? That'd be in meters per second. 32 times 5. If this car continued this type of motion, how far would it have traveled in 60 seconds? So we can use our how far equation. We can say, well, how far would this car travel if it traveled this way, accelerating this much? So we could say 1/2 times our acceleration times our time. Well, we're what, 60 seconds. Again, we need to square that. 1/2 AT squared. So that would be then 0.5 times 32 times 60. We need to square that 60. We get 57,600 meters. That's a lot of distance, right? So if this car continued this type of motion, how fast would it be traveling? Well, that would be VF equals VI plus AT. Again, we'd say 32 times your 60. That would be your speed. 32 times 60. And we get around 1920 meters per second. Will that get on there? I'm hoping it did. Well, let's go to page 2 here. And I'm going to put a little piece of tape down so it holds my sheet. And okay, a train moves with constant acceleration. At one point, it has a velocity of 20, and 300 meters later, or further down the track, it has a velocity of 40. So what are some important things I can circle? Well, the 20 is important. So what concept is that? Well, that's the initial velocity. This picture has V sub O. I've been using V sub I. Okay, not a big deal. Okay, further down the track, it has a velocity of 40. So that represents the final velocity. 300 meters would represent a displacement, or a delta x. Well, so in this case, let's kind of write down our equations. We have our how far equation. We have our how fast equation. Oops. VI plus AT. Okay, well, we know the VI is 20. And do we know anything really about time here? No, it's not giving us any time, so we're not sure what that is. 1/2 A. Do we know anything really about the acceleration? Well, that's kind of what we're trying to find, right? What is the acceleration? And again, we know this occurs in 300 meters, so we're going to equate this to 300. Well, can we really do anything with this equation at this point? We don't know A and we don't know T. So this equation is non-solvable, right? Because it's got too many unknowns. Well, let's take a look then at our velocity equation. We know the final velocity is 40. The initial velocity is 20. Again, we're not really sure what A and T is. Okay? Now, using the two equations we have, we really can't solve the problem. Well, let's take a look at maybe another type of problem. And let me kind of scroll up here, make sure this gets on here okay. And let me put down my tape again. A spaceship moves at an initial velocity of 10 meters per second. Okay, so that'd be your VI, right? That's what the spacecraft is doing initially. It starts to accelerate at point 1. So there's your A. How fast will it be traveling or going after it's traveled 5,000 meters? So this would be a delta X. So what is it we're really trying to figure out? How fast, right? How fast? Well, let's write down our how fast equation. Okay, we'd like to figure out how fast. Its initial velocity is 10. The acceleration is 0.1. And then we have our time there. We're not really sure about time. So there's our VF. So again, we've got kind of two unknowns here, right? We don't know what VF is. We're trying to figure that out. We're not really sure what time is. Well, let's write down our how far equation. Well, we know this is 5,000. Our V is 10. We said 10 meters per second. Okay, you see what we have here? We've got this equation, and could we actually use this equation to find t? Yeah, we could. It would involve then doing a quadratic equation or doing some factoring or something like that. So that's pretty challenging. That would take us a lot of time. So, you know, the question is, what's really common? You know, what's really common about these two problems? In this first problem here, the top problem, we really have two unknowns. We have two equations, two unknowns. We could work that out. It would take us a little bit of time. In this problem here, we've got a quadratic scenario here, which would take us a little bit of time. So what's really common about these two problems? Do you know? These are both more difficult problems. Well, the commonality really here is we're not really sure how much time it takes for either the train to move or the spacecraft to do this motion. So we're unsure about time. Well, it turns out that there's another equation that we can generate, and we can kind of helps us out when we're not sure about how much time it takes for an object to do some type of motion. So let's go to page 3. Well, the math involved here is pretty challenging, but basically what we're doing is we're going to do what's called substitution. And we're going to substitute, we're basically going to take this how fast equation and solve it for t. And then we're going to plug all this in, we're going to substitute all this in for the time on the how far equation. And you can see there's quite a few steps involved here. I wouldn't be so worried about the mathematics, you know, but I just kind of wanted to show you the steps. Well, at the end of all this algebra, we get then an equation that kind of looks like this. VF squared equals VI squared plus 2A times delta X. Well, VI squared represents the initial velocity, and we've got to square that. This represents the final velocity, and we've got to square that also. The A represents the acceleration, and the delta X again represents the displacement, or how far does that object move. Well, the benefit of this is what we call our third acceleration equation. So the question is, what's the great thing about this equation? Well, the great thing about this equation is we've removed time. Okay, we factored the time out. Okay, we were able to solve for time here, and we factored it out, and it's really useful whenever we have problems that we're not really sure about the time involved for an object to do something. So let's go back to this page 2 here, and let's think about this first problem, this train problem. Okay, Well, we said we know the final and initial velocity. We know then how far. We're not sure exactly how much time. So let's write down this third equation. Now, this equation has, if you look at this equation, it's got initial velocity, final velocity, and acceleration and displacement. Okay? So we've been calling our equations either how fast or how far. Well, this equation really doesn't have a name. I kind of name it the timeless equation because it's an equation that works when we're not sure about time. So let's see what we've got here. We've got the final velocity is 40. We're going to square that. We've got the initial velocity is 20. We're going to square that. How would you solve this algebraically? Well, let's square 400. So again, you might need a calculator to do some of this stuff. So we're going to square 400. That's 1600. And we've got 20 squared. That's 400. Don't need a calculator for that. Plus 2 times 300 is 600A. Can you work through that now? We can put the 400 on the other side, and that gives us 1200 equals 600 over A. And divide through by 600, and we get an A then that's equal to 2. That'd be meters per second per second. Okay, look how easy that was. So had we had to do all this stuff here, that would have taken us quite a bit of time. But we have now this third equation that makes it pretty easy. Let's take the spaceship problem. So we want to know how fast it'll be traveling. Well, let's again write down the timeless equation. Okay, we'd like to figure out how fast. Well, we know the initial velocity was 10, so we'll square that. The acceleration was 0.1, and the delta x, how far, was 5,000. All right, do you see how that works? Not too hard now, is it? So what we've got is 10, we'll square that, and then we'll add that to the product of 2 times 0.1, and then times 5,000. We get 1100, but that's the square of speed, so we'll need to take a square root. And so I get about 33.2. That the final velocity is about 33.2. So it started at 10 meters per second. The spacecraft accelerated for a distance, and we now get a final velocity of 33.2. You see how that timeless equation kind of works? It's pretty spiffy. Well, let's go now maybe then to page 4, and let's maybe work a few more problems together. All right? Are you up for that? I sure am. I hope you're doing fine. Isn't it kind of fun to work story problems? Yeah, you're getting better at it, aren't you? Again, I like to circle things that are important. Okay? Michael jogs at a velocity of 2.5 meters per second. Okay, so what exactly is that concept? Okay, that's a speed, right? That's what he's doing. That's an initial velocity. He then accelerates at a constant negative 0.1 meter per second. So that represents our acceleration. Now notice that's negative. So what's Mike doing? Well, he's slowing down, right? He's getting slower as he's jogging. Maybe he's getting tired, right? He's slowing down a little bit. So how fast? So that's VF. We're not sure what that is. That's what we try to find. So how fast will he be jogging when he's moved 10 meters? So that represents our delta x, all right? Now, do you see anything in this problem about how much time it takes him for him to do this? No. So if you don't really see that, if you don't see anything about time, then again, it's kind of nice to write down then the timeless equation. Don't feel like you need to memorize these equations, but you do know how to. You do need to know how to use them, right? So we're not sure what his final velocity is. We know his initial velocity is 2.5. We're going to square that. Plus 2 times a, well, that's a negative 0.1. And he then jogs for 10 meters. Okay? So, again, calculators are pretty handy. 2.5. I'm going to square that. And then I'm going to add it 2 times negative 0.1 times 10. Okay, it looks like he's going now at 4.25, but again, that's the square of his velocity, so we need to take a square root, and that's around then 2.06 meters per second. Okay, so he was jogging at 2.5, he gets slower, now he's at 2.06. Okay, let's take the next one. You might want to try this one kind of on your own. A bicycle rider pedals with constant acceleration of 0.5. Okay, that's an A, right? That's positive. That means he's getting faster. All right? Okay, he does this for 200 meters. So what's that? Well, that's your delta x. That's how far. If his final velocity is 15, okay, there's his final velocity. What was her initial velocity? Initial velocity. Okay? Do we know anything about time in here? No. So that should lead us then to the timeless equation. Square of our final velocity equals the square of our initial velocity plus 2a delta x. Well, we know the final velocity is 15, but again, we have to square that. We're not sure what the initial velocity is. The a then is 0.5. Okay, the delta x is 200. Okay, so can you work this out? So take your 15 and square it. Okay, so that's going to be 225. Take your 2 times 0.5 times 200. That's 200. Okay, do you know how to work this? You put this on the other side, then take a square root. So 225 minus 200. 25, take a square root. So 5 meters per second. So she was initially going at 5 meters per second. She gets faster. She ends her biking at 15 meters per second. She speeds up. Okay, let's maybe do one more here. A driver in a car is traveling at a speed of 31.3. Okay, that's the VI. The driver sees a deer 101 meters away on the road. So there's your delta x. Calculate the acceleration, the constant minimum acceleration that's necessary for the car to stop without hitting the deer. So we've got this car here. We can make a little diagram here, maybe a little picture. We got this car and then this deer in the road. And again, I'm not really very good at drawing deer, but there it is. Okay. So this driver sees a deer and has to slam on her brakes, right? So she's getting slower, right? We don't know what that acceleration is. That's kind of our unknown. So do we know anything about time in the equation? I don't see anything about time. So that means we need our third equation, right? Our timeless equation. Okay, well, we know the initial velocity was 31.3. Our final velocity, well, what is our final velocity? We want the car to stop, right? We want the car to stop, so our final velocity would be 0, right? So that's going to be 0. And you know when you square 0, it's still 0, right? So 2a, that's our unknown, and the deer's 101 meters away. Okay? So what we have to do is square that 31.3. Okay? That's 979.69. We'll put it on the other side, and that becomes negative. And we have 202a. So we'll solve for a. And we get then a negative 4.85 or so. Okay? So that's the acceleration needed to slow down this car so the driver won't hit the deer. Okay? Hey guys, good job. Boy, it's great. We got through some story problems, you know. Make sure you kind of use some of my techniques if you need to. Circle, underline things. Make sure you know how to use our equations. We've got this third equation that we can now use. It's called our timeless equation. All right. Hey, talk to you later, kids. Bye.